My name is Mike Goeke. I'm a senior solutions developer at Leading Edge. By day, by night, I'm a self-proclaimed maker and DIYer. And you are all here to learn about how I made this BB-8 that's sitting up here. So let's get started. Not getting any sound. Technical difficulties. We'll get it figured out. It's plugged in. Oh yeah, do you want me to unplug this? Here, maybe we can just start that over again. Let's see if it works. All right, so after that lovely intro there, we'll hit up on the major topics that I'll be going over today. First thing is we'll hit on some robotics. We'll do some talking about 3D printing, some prep and assembly, and then we'll hit up some hardware, and then finally some of the programming that's involved with this. So with every project, it's good to have some goals in mind. When I set out to build this, I had a number of goals. First goal was, first of all, let's build something that works, right? Let's build a robot, let's make it roll, let's make it talk a little bit, maybe have some flashy lights, just something tangible and something that works. I wanted to be able to gain some kind of understanding of robotics and how to program robots, and as well as their hardware components that are involved with them. I also wanted to use this as a project to introduce my kids into STEM. You know, let them get have them have a hands-on project where they could get into some of the sciences and engineering fields and gain some understanding of that. And then finally, I wanted to have some fun, right? Everybody wants to have fun in everything that they do. So with these things in mind, let's talk on some of like robotics. So what exactly is a robot? Well, a definition of it is it's some kind of electromechanical device which is capable of reacting to its environment in some way. So it's electrical mechanical device. So a toaster is an electromechanical device. Does that make it a robot? Well, not really. A toaster can't really interact with its environment through various sensors of that. Now it might be with all the smart homes and that are going on nowadays, but a basic toaster, no go. It's not considered a robot. What kind of components are in a robot? Well, first of all, you're going to have some kind of power source. We'll have to have some kind of actuation, you know, whether that's motors or actuators or air muscles, something along those lines. And then finally, A big component of robotics is it's going to have some kind of sensing involved with it. It's going to have to be able to sense something in its environment and be able to interact with that. So now that we have a basic understanding of what makes up a robot, let's talk a little bit about the initial design. So initially I thought, well, let's just get a gigantic beach ball, paper mache it, slice it in half, throw some electronics in it, we got a robot, right? Well, you know, after fiberglassing it and then putting some Bondo filler on it to kind of smooth it out, and then spending 20 plus hours of sanding it with a belt sander, it was sometime around that point that I was kind of like, you know, I have this 3D printer, why don't I just 3D print the whole thing? So I thought that, you know, that's a good idea. So I joined a club online called the BB-8 Builders Club, and if you join that club, hey, they have engineers and designers that are part of this club that have free 3D models that you can just download and then start printing. So I said, sweet, let's get those files, let's start printing them out. So speaking of 3D printing, what the heck is 3D printing? Well, right? What's this thing you're calling 3D printing? Well, at a high level, it's a process of taking a 3D computer model and making something tangible out of it, something that you can actually feel and touch. The way it does this is it takes a big spool of plastic, and it's going to force that through this hot end that melts that plastic, and at the end of the day, it's going to create some kind of part or a prototype or whatever your design is. Why is this so awesome? Well, in my mind, you can take anything that you can imagine, you can design it, and then you can print it. Is that just not a cool concept? That is just awesome. So now you're probably thinking to yourself, sweet, if I can design some things and I have a 3D printer, I can make anything, right? You bet. So let's kind of talk about this 3D printing and a little bit more of like the process of it. So like everything else, there's a process to everything, right? So with 3D printing, you're going to start out with a 3D model that maybe you design or somebody else designs. And you might design it in some kind of CAD program like Fusion 360 or SolidWorks. There's also some other free ones online like Tinkercad, and then there's some paid ones. Just got to find what works for you. Then you go through the process of taking that model, and you have to convert it into some kind of instructional language that your 3D printer can interpret. So that's through a process called slicing. And that's another software program that you use. You import your model into that, and you configure some settings and click a button to say go, and that software program is going to run through all these algorithms, and it's going to calculate out what is eventually called G-code. And G-code is really nothing more than a step-by-step instructional guide that's going to tell your printer, hey, go to this XYZ coordinate on your print bed, and while you're doing that, hey, why don't you spit out this much filament while you're doing that? So, and you get that G-code, you're going to plug it into your printer, and then we can print something. We can create something. Once you're done printing it, you may have some post-processing that you have to do. You may have had to use some supports, and those will be required to be cleaned up. There may be some sanding that you might have to do, some light sanding. And then, depending on what you're making, you may want to prime, paint it, clear coat it, whatever to make it look awesome. So we know how the process works. We know that we have to slice up our design and then we can print it. Well, what are we going to use to print this? Well, I keep mentioning this thing called material, right? So with 3D printing, there's tons of materials that you can use. This is just a high-level list of some of the more common materials that you'll find with a 3D printer. You know, you've got your polylactic acid, you got your acrylonitrile butadiene styrene, polyethylene terephthalate, various flexible filaments. You even have some specialties where filaments are laced with carbon fibers, high intensity polystyrenes, you've got some wood fills, you've got some PVAs, which are really interesting because those actually dissolve in water, so they generally are used for support materials, where once you're done printing, you can just dunk your printed part into a bath of water. The materials will eventually dissolve away. Let's take a little bit deeper dive into each one of these types of filaments and some of their characteristics and considerations. So PLA is the most common, it's usually the cheapest, and it tends to be the easiest material to print with. I'll say if you went out and bought a manufactured printer and it came with a spool of filament, I can pretty much put money on it that it came with a batch of PLA filament. It has pretty good strength, it's somewhat flexible, it doesn't require a heated surface in order to print with it. However, as a drawback, it has a very low melting point, which means that if you are printing a special cup holder for your car and it's very hot outside, you may come back out afterwards from work or wherever, and your cup holder may actually be a pile of goo. So it does not withstand temperatures very well, so you've got to kind of keep that in mind with whatever you're going to make. ABS, on the other hand, also has good strength. It's somewhat flexible, but it has a very high durability, and a lot of that has to do with its higher melting point. This particular type of material will not deform in your car on a hot day. However, it tends to be pretty difficult to print with, and a lot of that has to do with the fact that this particular material likes to shrink while you're printing. So as it's cooling down, if it cools too fast, it will shrink, it will warp, and that causes some issues while you're printing that you kind of have to be able to deal with. Some interesting facts about ABS is that Legos are actually made out of ABS. So when they injection mold Legos, they're actually using ABS. Another interesting thing about ABS is that ABS will actually dissolve in acetone. So what you can actually do is you can actually use acetone as part of your post-processing cycle. And some people, what they're doing is they will actually make a slurry of acetone, and they'll use that to weld parts together. You could use the vapors from acetone to smooth out your prints to eliminate your print lines, and it actually will make it look very much like an injection molded part. Some very interesting things that you can do with ABS in that regard. And then we come to what is probably my personal favorite for filaments, and that's PET. This filament is quickly replacing your ABS filament on the market as the choice for durable prints. It's strong, it's flexible, it's not quite as durable as ABS, but it's pretty close. It doesn't shrink as much as ABS, but more importantly, it's pretty easy to print with, which makes it a fantastic substitute for ABS materials. Most PET filaments are actually a copolymer. So you have your PET, and then that's spliced with some other molecule. And that's where you'll get a filament like PETG or PETT, where the last letter after that PET is what it's spliced with. So PETG is spliced with a glycol molecule in order to get your PETG. However, with every filament, there are some drawbacks. In regards to PET, it's very hygroscopic. And what that means is that it absorbs moisture out of your atmosphere. Actually, the second roll of PET that I purchased, I had to bake in the oven for about 4 hours because it was saturated with moisture from the factory. And when it's saturated like that, you can't get good prints out of it. Your layers aren't adhesing very well, and you'll just end up with a lot of gaps and potentially bubbles in your prints from your hot end evaporating the moisture out of it as it's extruding your filament. So it is possible to throw these in the oven, bake them at about 170 degrees Fahrenheit, 7 degrees Celsius, somewhere around there for about 3 or 4 hours to get the moisture out. This is probably fairly common with types such as PET and some flexible filaments. PET filaments tend to bond extremely well, which is also great for printing. Not so great for glass print beds. So there are a lot of people that will print with PET, not realize this, and then when they go to pull their part off their print bed, they will also yank out shards of glass from their print bed. So probably not an ideal situation, but it does happen. You have to be aware of it. You need to have some kind of release agent between your print and your print surface in order to be able to get that part off afterwards. I personally have pretty much gone strictly to printing on blue painter's tape. The PET comes off the blue painter's tape quite well, and if it doesn't, it's blue painter's tape. I can just use some sanding and sand away the painter's tape, right? So it's not a big deal. This sort of material also tends to be very ooey. It's very gooey, it's kind of globby. I really say that it's a bit boogery. When you're printing with PET, you're not exactly like forcing the filament onto the print bed, you're kind of letting it drop onto the print bed because of how gooey it is. Moving on to flexible filaments. Like the name says, these are flexibles. These are your nylons, your TPEs, your TPUs. These are materials that are strong, flexible, and durable. However, they are notoriously hard to print. And that has a lot to do with the elasticity and the flexibility of the material. As you're trying to push this material through your hot end, it's bending and flexing and trying to go wherever it easily can. Flexible materials can commonly be combined with other materials, which make for an interesting and unique situation that is more so for flexibles than other materials. So for instance, you could be printing out a wheel and you could print the tire and the wheel hub during the same print if you have dual extrusion with a flexible and a more rigid material at the same time, which makes your printing time less costly because you're not printing two parts, so you don't have to set up and tear down from every print. And it also fuses those two parts together, which is going to overall make them more rigid. So now that we kind of have some newfound knowledge on various printing materials, why don't we kind of go over some of the parts that are part of this BB-8 robot and what materials I used for each of those. So what you're looking at here is the skeletal system of the bot, and this was made up of 24 different ribs, and they all go together in triangles, and this was printed out of PLA. This was partly due to me being an inexperienced padawan when I started doing this project instead of a master, and I knew PLA, it was cheap, and it was pretty easy to print with, so it seemed like a good solution to start printing this robot with. The side panels and outer panels were also made with PLA. By now, when I got to this point, I had been printing for probably a couple months now, and really starting to kind of hone my craft. And that led me, just like Jedi younglings, they'll eventually grow out of their training lightsabers and they're going to get the real lightsaber, right? So I started moving into some more advanced materials. The drivetrain here was printed pretty much entirely out of PET. And then there are some drive gears, and the antenna on the robots are actually printed out of TPU, which is a flexible materials. I did experiment with printing belts out of flexible materials. I didn't have a whole lot of success with that. They just didn't have enough grip on the gears. I think that if I would have gotten a more elastic material like a Ninja Flex or something like that, something that's a bit softer, I think I could have had more success with that. I plan to explore that a bit more later on, but for the purposes of this, I ended up just finding the right size and buying a belt. The antennas were at first printed out of PLA and then ABS, and then I got tired of them breaking. So I ended up printing both the antennas out of TPU so that my kids would stop breaking them. So like most Padawans who learn new skills, there are lessons to learn along the way, right? So some of the lessons that I've learned. Monitor your prints. It only took one time that I didn't watch my print, or at least check in on it for a long period of time, that I clogged up my entire hot end, and I woke up in the morning and I had this giant goo of hardened plastic that used to be my hot end. And so what happened was I went to bed at night and I kicked off a print, and when I woke up, at some point during the night, the printer let loose of the bed, attached itself to the heat source, and then the printer doesn't know any better, so it just said, I need to keep moving and I need to keep dropping this filament, and it kept dropping the filament on the part. And at the end of the day, it was just a giant block of plastic. After a couple of days, I finally managed to break it all away and get my printer back. And then probably a day later or so, I finally got it back up and running. So I learned a valuable lesson and hit the ground running and ready to do some more, right? Next thing is, unlike Yoda in a lightsaber battle, 3D printing is extremely slow. There are a lot of parts on this that took 10 plus hours to print. There are some parts in this that took 20 plus hours to print. It is not a speedy process at this time. As the technology advances, I'm sure that we will continue to push the bounds of those speeds, but right now, expect to set something off and then check in on it for the next probably 3 or 4 hours at least until your print is done if you're going to start 3D printing. Next, it's an iterative process. This took me a little while to actually kind of grasp, is that, yeah, I'm designing these parts and I'm printing them, and they may not come out perfect the first time. Matter of fact, they probably won't come out perfect the first time. I mean, you're measuring in small metric millimeters, and things are just going to be off. So I eventually migrated to doing a lot of prototyping, where I might design something, start printing it. I might only print half of it, or I might only print a quarter of it, stop the print. It's not a whole lot of plastic that I wasted, but I can then start checking fits and adjusting my design to fit things perfectly. So, like Jar Jar Binks in the first 3 episodes of Star Wars, you're also going to have failures. And some of the failures that I had was ABS warping. This was a dome that I redesigned to be a single piece instead of 3 separate pieces. And it came off the bed on one corner. I didn't have the bed hot enough, and it warped, which rendered the part useless. At least I couldn't magnetize it and put it on the bot anyways. This part I ran out of filament. I wasn't watching and I ran out of filament, so it's only half a part. Not much you can really do about that. I have had marginal success in measuring out the height of the part and calculating out which layer I would have been on, and then modifying my G-code manually in order to try and finish it out. Sometimes that works, sometimes it doesn't, just kind of depends on the part. And then you have my personal favorite, the spaghetti. I've had this happen a couple of times. Part lets loose of the board, falls over, printer doesn't know, it keeps pushing out plastic, and it has nothing to adhere to because 3D printing is all done layer by layer. So if you're dropping one layer on top of the next layer, that bottom layer doesn't exist. It's just going to extrude out into space, and you end up with spaghetti. So real quick, I'm just going to kind of go over some of these parts and show some pictures and maybe talk a little bit about some of the prep and the assembly of it. This is what the dome looked like before it was printed. Before it was painted. It was printed out in a red PLA. All these files, like I mentioned earlier, come from the BB-8 Builders Club. They also have pretty good documentation on how to assemble it all and what optimal print settings are. However, what I've come to find out is that just because the print settings are good for printer A, they may not be good for printer B. So you're still going to have to do some experimentation and tweaking of the settings on your own particular printer. This is just some painting. It's what it looked like when it was finalized. One thing that I'll say and note about painting is that if you choose to use spray paint while you're painting, take note of the temperatures on the can and then probably add 20 degrees onto the low end of that temperature in order for the paint to actually work well. I had a lot of issues where the spray paint was yeah, this works fine between 50 and 70 degrees. And when it actually got down to about 50 degrees and I was spray painting in the garage, the paint was turning out terrible. I was getting all sorts of bumps and breaks and cracks in the paint. So those are all parts that I plan to repaint in the summer when it gets a little warmer. This is just some of the skeleton. Again, this was made out of PLA. More of the skeleton. Some of the outer shells. And most of these parts were glued together or fused together with screws, like nuts and bolts. And this is the final look of the ball. So we've got a shell. We have what's going to be the beginning of our robot, right? But it doesn't really move or anything. So let's get it to move. So let's talk some about actuation and some of the drivetrains. I didn't really have any problems actually assembling the bod and putting all the nuts and bolts in and gluing things together. That wasn't really any problems. The first problem that I actually encountered with this, the first major challenge, was the drivetrain. I went through 7 or 8 different iterations on drivetrains before I finally settled on one that worked. And even then, I ended up doing a number of redesign and customizing of parts in order to get it to actually work. A lot of this stemmed from the fact that my printer was not large enough to print these files out full size, so I scaled everything down to 80%, which means that this is actually an 80% model and not a 100% sized model of a BB-8. As a result of that, I ended up having to spend a lot of time doing the custom design of various parts in order to fit them in, because I couldn't just go buy a VEX gear or a VEX drive shaft or anything like that from online or from some kind of robotics store, because they didn't have the size that I needed. They were too big to fit in the cavities that I needed, so I needed to custom design those. In talking about drivetrains, as far as people that are building these robots, there are 3 main drives. You've got your hamster drive, or in this case, the cat drive, which is exactly what you think it is. It's some kind of mechanical device inside of a ball that drives up the side, and with its weight, it pushes it down and allows the system to roll. This drivetrain, through personal experience, will only work on smooth surfaces. So the files that are available through the club are not a smooth surface. So this drive, I tried to get this drive system to work with the actual skeletal system that I have here, and it did not work. The wheels continued to bind up, they got stuck, and they just spun sometimes. So it was not a viable solution for anything other than a smooth sphere. The next drive system is the wheel drive. This one is made pretty famous by a guy named James Bruton, who's a YouTuber. He's made 3 BB-8s to date. Every one of them has been this wheel design, and it starts out with a wheel hub, and you just build out from there and make it into looking like a ball. Then we get to the most advanced drive system, and this is the axle pendulum drive system. This is actually the drivetrain that, it was on the red carpet BB-8 that Disney, well actually it wasn't Disney at the time, but that was built for the release of The Force Awakens. This is also the drivetrain that I went to for the bot that is sitting down here. And the way it works is you have an axle, you have motors that circulate that axle, and then you have a pendulum system down on the bottom that kicks weight to the side in order to have the bot turn. So if it wants to go to the left, it's going to throw the weight to the left and force the bot to move to the left. If it wants to go to the right, it's the opposite. So now that we've chosen a drivetrain, it was time for me to start looking for some of the muscle, right? The motors. Let's look for something that's going to actually make this thing work and actuate. So we already kind of hit on what actuation is. That's your motors or whatever's going to make your thing move. Before you can actually select what type of motors you're going to use, whether that's motors or air muscles, you kind of need to know what kind of motion that you're dealing with. Is that going to be, are you going to be dealing with a lifting motion, Or are you going to be dealing with, in our case, just regular rotation and movement? What are the precisions that you need to be within? Do you need to have something that's very precise, like a 3D printer? It needs to have very precise motions, which is why they use stepper motors, because those are very precise instruments and very precise actuation. In our case, we don't need any sort of precision. We just need something to spin. So I went with DC motors and servos. Seemed like a pretty viable option. Through my research, there were three main things that you had to consider when trying to determine what type of motor to get. And those three things are your stall torque, which is the force at which your motor will no longer turn. You have to consider what voltage your motor is going to be at. Is that 12 volts, 16 volts? Is that 24 volt? And then you have to consider what kind of rated current it's going to produce. All these things are going to play into your other components of your robot, your power source and your motor controller, which we will touch on now. Motor controllers. This wonderful piece here is an intermediary electrical device that really provides power to your microcontroller and your motors. Microcontrollers can't normally push out enough power to drive a motor. I mean, if you're running a 12-volt motor, an Arduino board is only going to push out 5 volts. That's really not going to be enough to give you any sort of juice. So you use a motor controller. You hook your motor controller up to your actual power source, your 12-volt batteries or your 24-volt batteries, whatever those may be, and then that can both power your motors and power your microcontroller. So in selecting a motor controller, I kind of already hit on some of this where you need to know what voltage your motor is that you're trying to drive so that you can pick a motor controller that will match that. Pick wrong and you may burn up your motors or you may burn up your motor controller, depending on which way the power is going. If your motors are drawing too much current because you didn't pick a motor controller that was strong enough, then you'll end up burning up your motor controller. If you picked a motor controller that can't supply enough power from your power source, then you may end up burning up your motors. Speaking of power sources, similar to the way a kyber crystal would power your lightsaber, we need some kind of power source for our robot. In our case, we chose batteries. And we actually have 3 separate power supplies in the system for the robot. There's a small cell phone battery that's in the remote control down here. And that battery is actually 3.7 volts. And I had to use a step-up converter to convert that 3.7 volts, boost it up to 5 volts in order to run the Arduino and the communication device that's in the remote. The body of the bot is running a LiPo battery. It's 2200 milliamps. And then the dome is actually running on a 5-volt power bank that I got from one of these tech conferences. So recycle and reuse, right? The maker's dream. So you can't really have a robot with any sort of without some sort of sensing. A real robot will actually have some kind of interpretation and take in its environment and evaluate that and then do something with that, right? That's what really makes a robot and not some radio remote controlled car, is that it has the ability to do that. Unlike humans, robots are not limited to their 5 senses. So they have sensors for tons of things, including carbon monoxide, which we cannot smell, taste, or see, but hey, you can design a robot that can. And then that robot can do something with that if you would like. In our case, we used a MPU 6050, which is a fancy name for an accelerometer and a gyroscope. This sensor will measure 6 degrees of freedom, so it will measure an XYZ axis for acceleration, deceleration, and then an XYZ axis for tilt. That's your gyroscope. This allows the bot to react to turning so that it can help stabilize, and also for forward and backwards momentum so it can help stabilize in those scenarios as well. So now that we have all this cool stuff, what's actually going to be the brain of this thing? And that's going to be our microcontroller. And for our case, I used Arduino. And there are 3 different Arduinos in this robot. Well, not 3 different Arduinos, but 3 Arduinos. We have 2 Nanos, which is the one that's being displayed here right now. There's one in the remote, and there's one in the dome. And I mostly chose the Nano because of its size. There isn't a whole lot of space in there. In fact, my hand can barely fit in the head, so you're very limited on the size. And I chose the Nano because it's small, but I still have a fair amount of pins to be able to use and connect to. And it still runs off the same 5 volts as everything else. In the body, we have an Arduino Mega. I originally started out with an Uno, and then due to some other things that came along, I ended up having to upgrade to a Mega so that I had more serial ports, which is involved with the communication, which I'll talk about a little bit later. So why did I choose Arduino? Well, one, I've never worked with Arduino, so it was an opportunity to really kind of explore it and learn it. They're fairly inexpensive, they're open source, they're very modular, and I found that the coding examples were pretty good. Every Arduino sketch or program is composed of two methods. You have a setup method, you have a loop method. I equate this to a video game engine. So if anybody has ever done any sort of video game development, it's very similar. Once you write this program, you're going to flash it to the board, and it actually lives on the board. So when you power it up, it's going to run your setup routine first, and that's where you're going to initialize any of your variables, define what your pins are going to be, whether they're input, outputs, whatever else you need to do to manage state, that sort of thing. This method is only going to be called once, and it's only when your board first fires up. Then you get to the almighty loop. This method is, as the name suggests, is called consecutively. So it's just going to be called over and over again. And your code in this method here allows you to change and respond to your environment or whatever you want your bot to do. This is essentially the action method. Whatever you want your bot to do, this is the part of the code that's actually going to perform that action. Again, lessons learned. Everything that we do, we try to walk away with some lessons. What are some of the lessons that I've learned while working with Arduino and kind of tinkering? Well, for one, debugging is a pain in the butt. It's not as nice as you C# developers, and I say that lightly because I'm also a C# developer who can pull up your fancy IDE and actually step through code and interrogate what your variables are. Yeah, there's none of that. When you want to actually debug your Arduino code, you're going to get really familiar with how to print out to a serial terminal and how to organize your variables in such a way that you can read them flashing by your screen at like 100 clicks a second. The good news is at least most serial terminals now allow you to pause things so you can actually kind of look and scan through things. But yeah, you will get very good at logging in order to debug your code. The next thing is really understanding the difference between an analog write and a digital write. This comes into play with the motors, and it's also going to come into play with what I call the talk LED. And the big difference is that for a digital write, it's very binary. It's either on or it's off. There's no threshold of how intense that pulse is. Whereas like for analog, and you can analog write to a digital pin if it's a PW, a pulse width modulation pin. With an analog write, you can actually determine your speed of your motor by passing over a different value between 0 and 255, or you can determine how bright an LED is going to shine passing over the same value between 0 and 255. So understanding that concept, which took me a little while to actually fully get a hold of, has really changed my dynamic of programming with Arduino. Next thing is always look for example sketches. I've found out that when I get a new sensor or a new component, almost all the time, if you check the manufacturer's website, they will have some sort of example sketch on how to use that piece of equipment, which comes in real handy. It has saved a lot of time and frustrations, and some things it might actually give you code to calibrate sensors, because some sensors actually need to be calibrated before you use them. For instance, the MPU 6050 that I have in here actually needed to be calibrated in order to determine what kind of offsets needed to be set in the code prior to using it, otherwise it was just going to throw wonky signals. And then finally, test your components. I don't know how many components that I've purchased that have arrived DOA, but there were quite a few that arrived dead. And unfortunately, I wired all those up and put them in the bot without testing them beforehand, which meant that I had to tear everything apart, rip it out, and then find another one, test it, and then install it. So always test your components. The good thing is that these components tend to be pretty cheap, but they don't always come functional. Communication. We've got our robot. We've got some sort of motion in it now. We've got a brain in it. But now we want to be able to tell it what to do as well. So we need to have some kind of communication with it. There's a number of forms of communication that you can use with Arduino. You can use Bluetooth. You can use Wi-Fi. You can use RF, radio frequency. I ultimately chose to use Bluetooth, partly because the modules were pretty cheap. That way, if I blew any of them up, they weren't really hard to replace. Whereas like the XB Wi-Fi modules are pretty expensive. They're like $40 a piece compared to the $3 Bluetooth modules that I have in there. And I didn't really get into RF at all because I felt like if I went into radio frequency, I'd have to buy a radio frequency controller and go down that whole road, and I didn't really want to have to do that. So we have 4 Bluetooth modules that are communicating in this robot. One is in the remote. That one communicates to a Bluetooth module that's in the body. And since Bluetooth is only a single point communicator, I can't communicate from the remote to the head if I'm connected to the body. So I have another Bluetooth module beside the first one in the body that is connected to the dome, and that allows me to send a signal to the body that then gets transferred up through the dome through programming. Maybe overkill, but hey, it works. Speaking of controlling, ultimately, like I kind of talked about already, I ended up deciding to just build my own remote. I felt like this was going to give me the most control over the functionality that I wanted, how many buttons I wanted, what those buttons functioned as, what they looked like, etc. I experimented with using a PS3 controller. Didn't have a whole lot of success with that. These are just some images of the process of actually building the remote. I did design this and print this remote. It does have a Bluetooth module in it. Like I said, it has a step-up converter in it to take that little tiny battery there on the right and convert it up to 5 volts so that the Arduino and the Bluetooth module can both be powered. And at the end of the day, this is what it looks like. So with that, why don't I think you guys probably want to see this thing work to some degree, right? So why don't we do that? So if the batteries haven't died, we should be able to get something going on over here. And let's see, I set. We'll try this so that the people in the other theaters can maybe see too. Hopefully that's displaying to the other theaters. I'm not sure. And I'm going to step off screen for a moment. Murphy's Law, right? Anything that can go wrong will go wrong. So this was working ahead of time, and now it's not so much. So let me just power it down and power it back on and see if we can get it to go. Hey, there we go. So we'll just leave that off for now. So what we have is we have a bunch of sound files on here, and as I push a button, he talks. And I just lost signal. One thing that I've found with these Bluetooth modules is that even though you set one up as a master and another as a slave, and you say, hey, only connect to this other MAC address, it doesn't always adhere to that, and sometimes it will connect to another one in the bot that I don't want it to connect to, which severs my communication. What's that? Yeah, or the other 50 cell phones that are sitting in this room. Yep, that's right. Mostly it connects to the other one that's sitting right next to it. Okay, well, I was hoping to be able to drive it around a little bit and show you guys that, but I'm not sure that that's going to happen. But you at least got to hear it talk a little bit. I am still working on this and making some tweaks to it. Eventually I would like to actually go back and do version 2. And in version 2, I'd like to make it full size, since like I mentioned earlier, this one is only 80%. So we'll give this one more try. If it doesn't work, we'll just call it a day on that. Yeah, okay. My guess is that a wire came loose somewhere, and I'll have to find out which wire that is and then connect it back up. But I'll have to do that at another time. So, sorry about that, but you got to kind of explore it a little bit, I guess. With that,
do you have a YouTube video of it working?
I do not, but I could post something up if you would like. That's entirely doable. I'll have to create a YouTube channel first, though. So, but you know what? Hey, it can all be done.
Do you have video on your computer of it working that you can play right now?
You know what? I have one on my phone that I might be able to play. Actually, you know what? Oh, we don't have internet down here, so even if I had one like out in the cloud somewhere, I wouldn't be able to pull it down. Turns out theaters are very bad for Wi-Fi. All right, just bear with me and I will
Hey Mike, how long did it take you all together, like from when you started to now?
So the question was, how long did it take me to complete this thing in the state that it is currently? I started this back in August and have pretty much lived and breathed this bot since then. So it's taken a long time. I've put a lot of hours into it. I could not actually throw like an actual like hour figure onto it about how much actual time I put into it. I can just say, hey, starting at the end of August, early September, I've been working on this pretty much every evening.
How much of the work did your kids do?
My kids did a lot of the paper macheing and that for kind of version 1 that we threw away. To their benefit, my oldest is 7, so they're not real old, but they do like to turn on the head, and it has like an auto routine that I can kick it into, and they like to turn it on and talk to it like it's a living being. It's actually kind of funny. And then they have put in a couple of the screws and bolts and that sort of thing along the way, but
Have you considered using your phone for Bluetooth transmission part?
I have. So that was another consideration on why I did the question was, have I considered using my phone for Bluetooth instead of doing a controller? And the answer is yes. That was one of the reasons that I chose Bluetooth as well, is that with it being Bluetooth and pretty much every single cell phone having Bluetooth, you could write an app that does the same thing that this remote control does, right? And then you just always have your controller with you, or if you put it out on the App Store, you could let your friends or other people download it and then be able to control it. So yes, that was a consideration and part of the reason that I went with Bluetooth instead of some other communication method. If you guys have any other questions, go ahead and fire them out while I'm looking for this video on my phone.
Is there any chance that just a number of Bluetooth devices will get their hand out or interfering?
I think that that's a good chance.
We could all go on an airplane within 30 minutes for a minute.
we can give it a try. I'm not gonna. I'm definitely willing to try it. I'm sure if I tinker with it a lot too, that could make it work too. It was just working. All right, I think I found the wire. So let me plug this one back in. Yeah, it's not looking very good. All right, well, sorry, it was worth a shot. Thanks, everybody. May the Force be with you. I understand that I'm doing Star Wars references at a Star Trek convention type